Hello and welcome to this new series on digital storage oscilloscopes and their use in automotive, truck and coach, and heavy equipment shops. In this first of a series of videos, I hope to take you by the hand and walk you through the basics of oscilloscope use and progressively take you to a point where you can comfortably operate a DSO without fear. So let's get started. My first question when teaching a class on electricity is, why is electricity so hard for a technician to learn? Invariably, almost 100% of my students will say, because we can't see it. I'd like to change that thought to, we can see it, we just need to understand our tools a little bit better. They can be our eyes into this somewhat complex world, and if we understand what they're trying to tell us, we can understand a little bit more about electricity and how it works. If we look back over time, we have made gradual steps in the industry to creating better tools for electrical and electronics diagnostics for our technicians. My first step into electrical diagnostics began with a 12-volt incandescent test light, which many of us have in our toolbox. It was a great tool. I could solve anything with this. It told me I have voltage, I could check for good grounds, I could even tell how much resistance I had by how bright the light was. Sadly, I didn't fully understand that it was nothing more than an indicator that I had some voltage, some current, but not sure how much of either. When electronics came along, I also found out that I could damage an ECM with this test light if I wasn't careful. Okay, the next step in electrical for me was to buy a multimeter. Seemed like the next logical step. I had an analog meter, but I soon found out that, like my test light, I could also cause damage to an electronic circuit. Apparently there's this thing called impedance, and it meant that my tools were not up to par for what I needed to do to test electrical and electronic circuits properly without damaging them. We'll get back to impedance later, but think about that one for a moment. As my education in electrical and electronic diagnostics in vehicles grew, I soon realized that my analog meter and my test light were no longer the tools of choice. So I saved my money and I bought my first DVOM. It had all the bells and whistles and high impedance, which is necessary when you're diagnosing electronics. This must surely be the answer. I can measure voltage, amperage, resistance, temperature, frequency, and a few other things because this new DVOM, like I said, has all the bells and whistles. I could read all these values, but I still couldn't see what I wanted to see in the circuit. And the DVOM is one of those tools that we can get a digital reference or a digital numerical value to show us what is going on in the circuit. But if something happens very quickly, a DVOM is not able to pick up on it. So there was just that little lag or, a piece of the puzzle that I still didn't have. My father and my brother were involved in electrical and electronics through their own jobs, and I had been introduced to oscilloscopes at an early age. And the oscilloscopes that I remember at that time were very large and kind of clumsy and awkward, and mostly only electronic people were using them. So in our industry, when these graphic meters or oscilloscopes started coming out, I thought this was great because now I could actually see electricity. I could see what was going on in my circuit. So when the first scopes came out, I grabbed one up really quickly and fell in love with learning how to use a scope. So imagine now you're a young technician on the floor, and it's back in the 70s and 80s. And if we want to look at ignition patterns and stuff like that, we have this great big scope that we have to drag across the floor to hook up to our vehicles. So down on the bottom here, you'll see that we have a lab scope. This was basically a benchtop model, and again, it was heavy. There was a lot of bells and whistles on these that were really hard to learn for a young technician, and not something that you would get used to very quickly. So most people would just walk away and forget it. So on the floor, we had these large scopes, and these scopes here were a little bit easier to look at ignition patterns and stuff like that. And this is what we got used to. So fast forward to today, and we now have the capability to take our cell phones and turn them into scopes as well. In terms of a modern shop where diagnostics are done daily on high-tech vehicles, an oscilloscope is almost a must. So in the automotive world, you'll see a lot of people using digital storage oscilloscopes. And in heavy truck and heavy equipment and motorcycle, not so much yet, but I'm hoping that will change. If I look back at the analog scope, one of the things that I want to mention there is that they have no capability of recording data. A digital storage oscilloscope, on the other hand, will read a waveform. You can actually monitor everything in real time. And the nice thing is that if I see something that I have as a known good waveform, I can take a snapshot of that and put it into a library. So I can take snapshots, videos, etc., depending on the capabilities of the scope. But the nice thing is you can take those snapshots, put them into a library, and keep them forever. The nice part about that is 6 months from now, when you run into something that you suspect is not right, you can go back and refer to a known good waveform in your library and compare the two. And we'll get to that way down the road. But so on this little scope here, this is a single channel scope, and it will monitor one signal at a time. This larger picoscope up here is capable of going up to 8 channels at a time, or 8 signals that I can watch at any given time. So there's these two, and there's all kinds of oscilloscopes in between. They're made by Handtech, Snap-on. There's all kinds of different companies out there making digital storage oscilloscopes for automotive and heavy truck use. So please take advantage of it. Don't be afraid of it. Just grab one and go. Okay, so let's say that you've gone out and you've purchased an oscilloscope, or you've borrowed one from your friend, and you want to see a signal. The problem with a lot of technicians when they first grab one of these scopes is they turn it on, they expect something to happen, and they have no idea what they're looking for. At the very worst, you're going to find some sort of random action occurring on your screen. If you're really lucky, you may find that you actually have a waveform on there, and it makes you all giddy because you can see something happening. Like I said, these are your eyes to electricity and electronics. So now that I can see a waveform, I have to start understanding what these waveforms mean. And I think this is where a lot of technicians walk away, is because they don't want to take the time to learn what I need to know about these waveforms. So basically they're broken down into 2 different types. There's an analog waveform and there's a digital waveform, which can also be broken down again to pulse width modulated waveforms. So let's have a look at these. Okay, so the first one I want to look at is an analog signal. An analog signal is one that varies continuously in frequency and amplitude over time. So the first thing I want to point out is our vertical axis is our y-axis, or where we want to measure voltage. Our x-axis, or horizontal axis, is for time. So we're basically measuring voltage over time. And this is continuous. It just keeps on going and going and going until you stop it. Okay. So having said that, if I look at an analog signal, it can change in frequency, which means the number of cycles per second. It can change in amplitude, which is the height of the waveform, or it can be amperage or pressure depending on what we're measuring, but I can monitor that signal for as long as I want. One of the things I see when people are teaching about signals is they look at that perfect sine wave and they refer to that as an analog signal, which it is. But it seems to stop there in a lot of training courses that I've seen. So what I want to mention is this: an analog signal can vary in amplitude over time. Okay, so in this picture here, I've got an example from a throttle position sensor. And this is basically me taking my foot and varying the amount of pressure I put on the throttle position sensor or on the pedal. So you can see I'm applying pressure, which means I'm getting voltage here, and then I level off, and here I'm letting up on the throttle, I'm applying the throttle, letting up on the throttle. So I'm just moving my foot up and down on the throttle and causing this pattern to occur. Now, how's that going to help me? Well, again, if I look at simple little things like this drop in voltage right here, and let's say this was supposed to be a very smooth transition up to full throttle, and then I held it there and it would move straight across. But right about this point here, my throttle position sensor dropped out. Well, I can see this visually on the scope, and I can understand that something happened to my voltage right at that point. So either I lost my voltage going into the sensor, or I lost my voltage in the sensor. So this is a nice little tool to help me evaluate what's actually going on there. And the thing about this is, if I were doing this with a voltmeter, I may have gone right across that transition without ever catching it on a meter. And you have min-max on some meters, some don't. Even on min-max, you might not catch it, and if you did catch it, you might not understand it. Right here on the scope, I can see exactly what happened. Okay, so let's look at a little bit of terminology for an analog signal, just so we have a little bit better understanding of it. The first thing I want to look at is the peak of the waveform. Okay, the second part is going to be the trough. So if I look at my waveform from peak to trough, I describe that as my amplitude, is basically the height of the waveform. The second part is the period. And the period is how long it takes to go from one start of the waveform to the start of the next waveform. So here's the start of one, there's the start of the next one. And that period is the amount of time that it takes for that to occur. The third one is going to be frequency. And frequency is the number of cycles that occur per second. So in this case, it's saying that I have 150 cycles per second. Hertz is equal to cycles per second. So that means that I have 150 of these waveforms occurs in 1 second. Well, you might look at that and say, well, there's only 2.5 that I can see. Well, if I were to change this waveform and change the time on it, I could actually fit that 150 Hertz into a single screen, but it'd be very tight and hard to read. So like I said, we can change the screen to manipulate that waveform to see what we need to see from it. I could expand this out to almost a flat line if I want to. That's a powerful tool. Okay, the next thing we want to look at is digital signals. And digital signals are obviously different from analog in terms of the fact that they have very discrete values. So we refer to this as a square wave pattern. And like I said, they're very discrete values, meaning that they're either on or off, they're high or low, they're ones and zeros, which is a binary characteristic. So when I look at this waveform, I start out here at 0. I turn the item on. Now I'm applying 5 volts to it, and I turn it off. I turn it on again right here. It's on, it's off. So there's only 2 values that this can have, on or off, 1 or 0, high or low. That's a digital signal. Now we want to look at pulse width modulation. And basically it's a technique that is used to switch DC voltage on and off at a specific frequency to reduce the amount of power used and the heat produced. It can be either constant or it can be variable rate. So let's explain it this way. So in the old days, we used to take and we would wire up a fuse, a switch, some sort of load, let's call it a light or a motor, and our power and ground. The problem is that when you wire something up like that direct, it's producing a lot of heat and there's a lot of energy that gets lost. So what they found was that if we very rapidly took and turned this on and off very quickly, we could reduce the amount of power used and also reduce the amount of heat produced. And this is happening in milliseconds. Okay, so what this means is that I'm switching this on and off very quickly. I'm not building up a lot of heat, but I'm getting the same effect. So whether it be a light bulb or a motor, nothing is going to change in the way it works. We can speed it up, we can slow it down. And I'm going to show you later on in later PowerPoint or later slides how we can achieve that, and there's no effect on what you see. Okay, the last thing I want to have a look at today for this video is the duty cycle. And the duty cycle is basically a ratio that describes the amount of time that the signal is turned on in comparison to the total cycle time. So basically refers to the on time. So let's look at our very first one here. And you can see I have a 25% duty cycle. It means that out of this period, from the start of this to the start of this, I have only about 25% of that total time where I'm turned on. The next one is a 50% duty cycle. And now you can see my on time and my off time are pretty much equal. So now I've got a motor that turns at half speed. I have a light that runs at half brightness, but that's my duty cycle. Lastly, I've gone to 75% duty cycle, and now you can see that my on time is much more than my off time. So again, it's running faster, and we can use this kind of a scenario to run things like blower motors. Okay, so duty cycle is a very effective tool. The other thing I want to mention here is that when you start looking at these types of signals, we can also start using them for carrying digital data, which we'll get into later on. Okay, to wrap things up, I just wanted to give you a quick review on the terms that have been used in this video. And I hope you enjoyed the video. If you do, please subscribe and please like the video. And there will be more to come. Go grab your oscilloscope.